Okay, let me go to the share the screen again, because it's a good question actually, and it's always never not important, especially this one. I mean, it's a big question for us from this point on. We really have to have a full understanding of it, because we don't have a handle over it. Namely, the fact that I have a cross product in here, A crossed with B is going to give me a vector C. As I said before, this you must have had it in physics 250 because it's extremely important. There are two versions of the right-hand rule. There is this version, basically, you take the first vector, and you probably need to practice it with your right hand, not with the left hand, okay? So if I open my palm the way I have it opened right now, that is A, actually. That is a vector A. When I tilt it, when I open it, when I take it to the other direction, that is a vector B. So A cross B. The result is the sum, C, okay? So A cross Did I lose you guys or something, or what?
Yeah, I think he lost us.
Okay. Where did we go? Where did the connection drop? You guys remember? Did I go through the cross product or not?
You were just talking about the right-hand rule with your thumb.
Okay. So again, let me repeat this. Okay, it's extremely important. Okay. So first of all, this is A crossed with B. The result is C. Another version of it, and it has to be the right hand, okay? I know for me, I'm looking at the screen, and I'm seeing what looks like it's my left, and that's because of the reflection. That's basically the effect of the mirror, basically. So again, this is A, this is B, and the result is C. So this is C. For Lorentz force, if I can get it in here, we have a scalar multiplying it. So we have F. Why is my screen not working right now? Okay, I think I have it now. So we have F equals to Q V cross B. Okay, because of this Q being there, Q can be positive or negative. If Q is negative, you have to reverse the right-hand rule. So you still use it. Okay, so you still use it, except that, are you looking at the screen or not? Or my screen is not shared again?
We just see the camera right now.
See the camera, okay, sorry. Sorry about the. Okay, why is this thing doing it today? It is not good. Okay, let me share the screen again. Okay, so this is Lorentz force. This is a big deal in terms of this chapter. F, this is the magnetic force, is equal to let me go to the draw tool in here, because apparently if I touch that thing there, it goes away. Okay, so F, in this case, this is the magnetic force, is given by the right-hand rule Q V cross B. You do the V cross B first, using the right-hand rule. So this is V now. This is B now. They don't have to be, by the way, perpendicular. This angle does not have to be 90 degrees. It can be any angle. So you're going to get a sine of this angle. Except if they are parallel, then it's going to be 0. Sine of 0 is 0. Or if they're anti-parallel, then it's going to be a sine of 180 is going to be 0. Other than that, any other angle will do. So sine of that angle, and then this is the direction of this cross product only, okay? This two, D cross B. If Q is positive, that is actually the direction of F. If Q is negative, F is actually in the opposite to that direction. You guys understand this? Yes? Okay.
Yes.
Okay, very good. This is important, and I cannot emphasize it enough. When we're dealing with current, actually, this rule makes more sense because the current curls, and as it curls, this is the magnetic field it produces, or we're going to talk about that, and we talked about that already, the effect of the magnetic field on the wire. Again, you have a wire that has a current running through it, and you have the magnetic field that is going to affect it. This is the direction of the current, okay? This is the direction. Now we have Julian with us too, so let me check the attendance again. Let me make sure that I didn't miss anybody. If I missed you, please let me know, okay? I have Aaron, Chad, Tim, Gareth, Sophia, Jonathan, Andrew, and Julian. I have everybody in here because I have Gino also. Okay, and who else? That's it. We're missing, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We're missing 4 people, I guess, or 3 people, I guess. Okay, anyway, this session is supposed to be recorded, and I don't know if it is or not, but if it's not, we will have to figure out exactly why it's not. Anyway, so this was a question about the right-hand rule. For those who did not join me before, I cannot also emphasize enough on the fact that you really have to keep up with 2 things. The one thing is more important than anything else, namely reading the chapter, okay? I know that Aaron posted a lot of the formulas that we'll be using in the discussion session. And let me again show you where that is, okay? Let me go into, stop the sharing of the screen again, okay? And go to share where is it? Share again. We're going to share this guy in here. And I'm going to go to, you guys see this? This is basically the screen that I'm sharing right now. It has to do with the with our session in here, with the canvas. Do you guys see that, everybody?
Yeah.
Okay, very good. Okay, in the discussion section, the button in here, okay, if I click on it, this is where everything is happening again. And I know that some of you already have been in there. That's very good. Some of you probably did not. I post a lot of recordings. This is basically the first, what is it? This is the first part of the chapter 27. The second part of chapter 27. It's supposed to be hopefully helpful in trying to get you to go through the lecture again. This is the third part. This is a short video, but this I couldn't cut it somewhere. So I was thinking to cut it, but the whole thing went on and on and on for about 41 minutes. So I'm relying on you guys that either you take some meal or something like that before you do that, or you cut this thing into different sections, basically. Good morning, John. If you put your name also in here. So you go, as you go through that, I want you to pause it and also think about that. And if you have any questions, it's a good idea to come in here and ask a question. If it has related to this one, and if it's a general question, ask the question in here. And I will know that there was a question in there, and I will try to answer it. And when I answer it, I will answer it in here. This is if the question is general question, okay? If the question is very, very specific to you only, you can always use the inbox, okay? Question, for example, are we going to do lab? Are we going to do a lecture or something like that? You can always ask it in the general questions in here. Chapter 28 already, I started on it. If I go back to the discussions in here, chapter 28 is already there, but I did not upload at least the videos yet. But I'm hoping that you did chapter 27 this week. Okay. I also posted, and it's still true, for the assignments in here. So if you go to the assignments, I don't know how it looks 100% honestly, how it looks from your end, but it's in, this is how it looks to me, okay? So chapter or the printed homework version 11 is here already. Remember that by rule, we're going to drop to the lowest two homework because they exceeded the number 10, okay? But I still think that it is very important that you do all of these problems and follow the same method that we did in class, namely that you justify, first of all, you gather all the information, what you know, what is asked from you as you solve the problem, justify the solutions, and then see if it makes sense to you or not, try to analyze your answer, okay? So to show understanding, basically, and you know what you're doing, okay? So that's something in here. And this is a file upload. I take any format that you're going to upload it in. If it's an image, please make sure the image is readable, okay? So that I can read it. If you can't read it, I can't either. So it has to be clear so that we can do this thing in here together. For the lab part, I'm working on the lab. Hopefully nobody submitted the lab yet because let me go. Oh, I don't want you guys to see everybody's grade. Let me exit this thing in here. Okay. Let me stop the sharing because that's bad. If you go back into that window in there. Okay, so everybody's here now. I see that we have 12. No, there is some person. One person is not here. One person is not here. Jackson is also here too. So let me make him present too. Okay, let me go back in there, okay? Okay, good. Okay, anyway, okay, so let me go back to the sharing because it's important that we talk about this. Okay, so we're still here. In terms of uploads, like I said, is you're going to be uploading your assignments as before. And one of the things that I'm working on, and actually it's going to apply from this lab, from lab 7 that you guys have in your hands. I'm going to make it, I mean, if you already submitted it, that's fine, okay? And if you think it's good, that's fine. If not, I have another form for you that I'm working on right now. And it's going to be a PDF fillable file. So it's much easier for all of us to work off of the same thing. Let me stop the sharing of the screen and let me pull the PDF file in here first. No, that's not the screen. Okay. Okay, so let me go back in here and share this screen with you so that you guys see how you're going to be doing the lab. So we're going to share in here. We're going to share this file. Okay. This is what is known as a PDF fillable file. So basically, it's the same old report that you guys do, except instead of having to basically fill it with pen, you're going to do it with a pencil. I hope you guys are familiar with this kind of files because they are common, especially if you did any kind of taxes or anything like that at some point. At least a few years back, they used to do this ones in here. Now everything is filled on websites and things like that. This is a PDF fillable file. What I want to warn you up front from it is do not use Chrome or Firefox or Microsoft, what is it, Edge, or any browser to edit this file. Because if you do, it's not going to save. That's the problem with it. You work, you spend a lot of time filling out all of this file, basically putting your name, the objective of the lab, everything in here. You're doing, answering the questions. I think that it looks immaculate, beautiful, and everything is correct. You come in here to the data table, you fill out all of your data table, and you answer all of the rest of the questions, and then you answer this question in here, and you answer this one. By now, you spent at least a couple of hours on this thing on a browser, and then here you fill out all of the data, and then you find you made a mistake. You come back, you replicate the data, and you fill this part in here. It's already an entire afternoon has gone by, and you're still working on this. You do this part in here. Just remember this. Now it's all finished. You did the conclusion, and you think everything is beautiful about this report, and you're doing it on Chrome or something else. and you send it, it's going to come out blank. And that is disaster. You guys understand the problem? So you have to use Adobe. It's a free software from Adobe, Adobe Reader. From Adobe, that one, you can save it. You guys understand this part? So I'm going to put this as a note. Do not edit it or save it in a browser because it won't save simply, okay? I think there are some modern browsers now that they caught up with this thing, but the vast majority of them did not, okay? I think probably Microsoft Edge, I think now is persisting data on your computer, but the others did not catch up with it, so do not try it. Do not even go there. It has to be done with your Adobe Reader, basically. Or if you have Acrobat, the full version that comes with it, that's fine too, but that costs money. It's a freeware, so you can download it, okay, and start working with it. If you opt not to and you would want to do it by pen, make sure you have a good scanning device that can read the information correctly and send it to you. So that's still option. That option is still available. So you still have this one as another option. Or if you want to, after you fill it, make sure you print it right away. If you print it right away, even from a browser, it's going to persist. It's going to print on your printer, then scan it again and send it, which is kind of defeats the purpose, but that's fine. Okay, if you do that. Now there are two types of fields in here. There's the red fields and there is not the red field. When you don't do highlight, this is how the file looks like. It looks kind of similar to any other regular PDF file. But when you see in here, it says highlight existing fields, it's going to tell you where you need to go and start putting information. So it's a good practice to turn on this button in here, okay? And that you will not also find it in the browsers. The browsers do not give you this feature. So you will see the file looks like this. But when you hover with your mouse there, it gives you the place where you can start typing, okay? And here you start typing. But this feature is much easier actually with Adobe. Adobe, which is dedicated software for this kind of thing. There are two kinds of fields. There is the ones with the red box around them and the ones without the red box on them. The ones with the red box are required fields. If you work everything and you forget to include your name or forget to put the objective or forget to put the conclusion, the file will not save. And that's another thing. So you have to do that. You have to start with three, the ones that are red marked. First of all, your name, so that I know which one submitted what, so that you can get a grade for it. The people who worked with you, I know from now on, we're not going to be working with the other people. So you need to, you can leave this part blank, but for this lab, the one that you guys are supposed to be submitting, your name has to go there. So without my name in here, I'm going to put my name in here, this thing will not work, okay? The objective in here is that of the lab. This is still the same rule as before. So this purpose of the lab was to what? Verify Ohm's law and do this thing and whatever the stuff in here, okay? That you wanted to do. Okay, this is text enriched. That means if you put some nonsense stuff in there or things that are not misspelled, it's going to help you, tell you that this is not spelled correctly, okay? So that's a nice feature, so that helps you if you get the typos fixed. Again, this is this objective for this part of the activity. The questions are the normal questions. If you encounter a formula and you would want to write it, you can write it however you want to. For example, V equals to R times I. If you like to write it this way, that's fine. Or if you want as I equals to, for example, let's write it in that formula, V underscore, if you want to write it this one, R underscore 1 equals to, and here epsilon, you can write it E if you like, or like epsilon if you want to, okay? Times R1 underscore 1 divided by open parentheses R underscore 1 plus R. Of course, this is not the answer to this question, but I'm just showing you how you can write formulas if you really have to write formulas in here. And if you want to write a number in here equals to 12.5 ohms in here, okay? So again, you don't need to do this. This is not necessarily the answer to this specific questions, but I'm just showing you if you have to write formulas, you can write it whichever way you want to, as long as it makes sense to you. And if it makes sense to me also, if I have a question, I will ask you about it. Then after you're all done with your data in here, I don't know how much was it. Let's say, for example, 3,450, and it's ohms. So at the end, we can probably add the ohms in here. I can't right now. If you try to add anything in here, it will not work, because this is not a fillable field, okay? So if you want to type in here, it's not going to work. I'm trying to type, by the way. You see the mouse clicking? Yeah. It's not working, but the fields that I can type are the ones that have this thing. Once you turn on the highlight existing fields, okay? Once you're all done and you did your conclusion and included data, specifically errors, how confident you are in your measurements and your conclusions, you're done, okay? Confidence, I don't know. Do I spell it right? I don't know. Okay, probably I did, because okay, that's good, okay? It's a helpful thing to do, okay? So it's 4.2%, okay, error. Okay, and the resistor resistance, equivalent resistance, I don't know. You guys are, this is your job, okay? Equivalent R is equal to, I don't know, 12.5 ohms, okay? So I did the conclusion, I wrote everything, I did everything in here. Now, notice something in here. This text can, if you write more than you need, if you need more than the space allotted, first of all, the text will shrink in size to allow you to put more and more. But don't make it so that the text is very small. If you think that you're going to need more space at the end, please continue, okay? And add another text file or a Word file or whatever you feel you need to add to continue your discussion. What I want you to do is, once you say continue, you need to refer specifically to either, I mean, if I'm going to continue from the conclusion and I have a document I need to attach, that document needs to say conclusion, added to conclusion or something like that, so that I know where to append that text, okay? So if you add, for example, question 1 is too long for you, it's taking too much space, and it's not giving you enough space in here before the question ran out of space, then in that case, you're going to add continue. And when you're answering the question, you're going to say question 1, continuation or continue, whatever you want to do, so that I know that this is added to question 1. You have so many questions per lab and so many labs. It's going to be hard for me trying to navigate my way and find which question you're trying to answer in here. In other words, you need to be, please, organized, okay? Other than that, you can use your own basically version, which is you will need a scanner and a good photo taking thing, and it's going to be, I believe it's going to be, this one is going to save time, okay? Okay, so this is one thing as far as labs. The other thing as far as labs is something else that I am working on, and we're not ready for this lab. This lab that we're supposed to do has 2 parts. The first part is the RC, which we did already in class. Let me stop this sharing. Does anybody have any question? And let me go to the chat session in here. Let me stop the sharing. Or is this chat in here? It doesn't show me that. Okay, probably, yeah. And the chat. Okay. I don't see any other chat questions. I know I put something in here. Oh, that's probably from before. Is there any question related to this topic, to this question, to this item? Now, granted, when you start working on it, you might have a dozen questions, okay? Please ask them in the discussion group, okay? Do not ask them in the email. Because yes, I'm going to answer your email. I'll do my best to answer everybody's email. And so far, I don't believe I have missed anybody so far. But try to answer them try to ask the questions in the discussion sessions. That way, everybody will benefit, because somebody else might have a similar question, okay? And they don't think about it, okay? And then once it's once they see it, then they remember that that's going to be a question that they should have asked. Okay, that question is a very good question, Tim, and actually I'm glad that you asked it because I was thinking to say that, but I forgot. Okay, sometimes that happens too. This file will be uploaded as part of your lab instructions. Okay, so if you go back to the lab, right now probably it's not there, but it's going to be uploaded there, and you will have for every lab its own specific fillable form. So this works only for this lab. Another lab will have a completely different form that has some required fields and some non-required fields. So that's the answer to that is in the lab. What is it? In the lab assignment. You know, when we have the assignment for the lab, there is always a section for it. And every lab assignment will have that file appended to it in the bottom. It says, okay, here is your fillable form. So here is the instructions. Here is the stuff that go with it. Here is the Excel file if you need that too. And this is the fillable file. Now, the fillable file will not have graphs. So if at some point you're required to graph, you have to use the graphing software. Excel is actually a very good graphing software. I'm going to show you today another tool that is actually an outstanding tool, and we'll be using it extensively for the lab. Anybody who's familiar with GeoGebra, that's good. If not, it's a good idea to get used to it because it's something that is going to be the website for GeoGebra is geogebra.org. It's a free software. You can download it even on your phone, but that's not a good one for the phone, okay? It's not as functional as the one for either online or the one that you can download on your computer. I think they stopped the downloads at some point. I don't know if they resumed it or not, but I have the standalone version. In other words, I work on activities and then upload them. So let's talk about GeoGebra because it's important, okay? If you have any more questions about this part, please, for the fillable form, please, you can ask it and then we will answer it there. I'm going to stop the sharing of the screen and I'm going to pull my GeoGebra. Let me make sure I have the correct one. Okay. Let me exit part of it, Okay. We go back into Zoom in here and share. Where is the, doesn't show me that. Huh. Oh, here it is. Okay, GeoGebra. Okay, GeoGebra, I'm going to hold this. Actually, I'm going to upload this to my own link, and I'm going to tell you where the link is going to be once we're ready for it, okay? So that you can go actually and work with this file as if you're doing the lab at home. I mean, in the lab, I'm sorry. But you're going to be doing it online. So this is an RC circuit. Does everybody see this RC circuit in the bottom here? I hope you do.
Yeah.
Okay, so you have a battery in here. Right now, the EMF is 24 volts. 24 volts, but I can change the EMF up to whatever value you're asked to do. So if I'm asked to run it 12 volts, I'm going to run it at 12 volts. So right now, it's running at 12 volts. So this is a battery source. The switch right now is closed. That means if I open the switch right now is closed. That means if there is a current, it's going to run. Right now, I just closed it. But if there is a current when it's closed, when it's open, I should say, the words in here are kind of backwards, okay? Okay, so the circuit right now is actually open, okay? So what that means is the current is gonna come in here and it's not gonna go anywhere. But if I close it, okay, right now, the word doesn't change. The capacitor is charging. Do you guys see that? Right now, the capacitor is isolated because it's not connected to anything.
Right.
This is open. This is open. So both of them are, there is no current running right now. And if I close it right now, the current is going to be charging the capacitor, comes through the capacitor, comes to the resistor, and goes back to the battery. I have made the resistor so that it never drops below 10 kilo ohms. Because if it's too small, this thing circuit that, okay? There will be a short circuit, so we need, at least for safety purposes, we need the resistor in here. So the minimum I assign for this lab is going to be 10 kilo ohms. I know the lab instructions ask you for 100 ohms and things like that. So I'm going to change the lab instructions to keep it with the numbers that I have in here, because I want this to run a little bit as slow as I can so that you guys can capture it, okay? So right now, I have tau, which is RT really. R times C is this much. Oh, I need to change this number. It's actually in seconds. It's in milliseconds, okay? So I need to change the unit. So it's 0.49 milliseconds. And this is how much we have right now, the capacitor. The capacitor, you can change it with different values. Notice how Qmax is changing in here. So a higher capacitor can store more charge, lower capacitor stores less charge. But tau also is changing, lower C, lower tau, and so on and so forth. Right now we're charging, supposedly we're charging. We didn't show the graph right now, so I'm gonna charge. I'm gonna start. Do you guys see the play button in the bottom? I'm gonna start charging. So I'm gonna stop the charger right now, or if you stop the time and open the circuit, okay? So right now, this is how much charge. It's not fully charged, but it charged some, okay? I can find the tau character. Remember, this is supposed to be an exponential, so technically I should find where the exponential is, and I can find where tau is and see if the numbers match. I have different values. Each of this is half of a millisecond. So this is 0, this is half of a millisecond, this is a millisecond, this is almost 1.5 milliseconds. So I can find the different values in here for the corresponding values as related to Qmax, and then see if it fits the curve or not. So this is fine. Let's discharge this capacitor right now. So we're going to close this circuit right now. So the current now will leave the capacitor this way, actually, because it's positive this way, and comes and goes around this way. I'm going to close this portion here and charge discharging in here. Okay, again, this is a discharge of a capacitor. So this part is, you guys have done that in lecture, and it should be something that we're going to capture in here. Okay, so we're going to collect data. It's going to be online for you guys. You're going to collect data and try to answer the question. Again, you're going to change different values for the resistor and see how that affects the curve, and so on and so forth, okay? And also, if we need to, we may have to change C, the capacitance, and C, the capacitance will play a role in terms of how much, right now it's max, how much the value of the maximum value is in there. Same thing also with this one, to give you more and more. So the part RC is ready, okay? The part RL, we are not ready in lecture, okay? Because we're supposed to be, the lab is gonna be on both the time characteristics for both the RC circuit and RL circuit. And because of this disruption that we had in lecture, and I'm not sure even if we didn't have this disruption, honestly, if we would have gotten to the inductance or not. But the inductance is the other part, namely that you will have, instead of a capacitor here, you will have an inductor, and that inductor basically will also have a buildup of a current in a similar fashion. And then as you switch from a different signal to another one, it's going to kill the current. So the current basically will increase and establish a value, and then it's going to decrease backward and there until discharge. So those are the lab that we're supposed to be doing. I hope you guys will have a chance to look at this software, which is a freeware. It's used extensively just with the basically chat. Is anybody familiar with this software from before? Because I wanted to know if anybody has used it already.
Yeah, I know Hanley had us use it, or showed us it in Calc 3 a couple weeks ago.
Okay.
But not the desktop version. She had used the web version.
Yes. The reason why I like it, it's really, for me, I can develop the activities at home, basically, and work on them. And once they're ready, I can post them into my online session so that you can guys go in and do your activities. And actually, if you have a desktop version, you can download them yourselves and start doing other things. This is actually an outstanding thing. You can solve differential equations with this thing. So this is really, it's used extensively more by math people than anybody else. And I know that I have lined up about several labs, actually so far about half a dozen labs for my classes. And if this thing extends way beyond this semester, that's probably the way to go for me for most of my labs, for all of my classes, including physics 252. If you guys are going to be taking it next semester. Okay. So this is basically the way to go, at least for me. There is another version, but that's very costly. I don't know if the campus can afford it or not. And that is MATLAB. MATLAB is actually a very powerful simulation software.
Oh, yeah.
Yeah, but and it has a component for called Simulink for all kinds of stuff that you can do for electricity and for everything, for not just for electrical, for mechanics, for all kinds of things that you can do. But at this point, this is basically what we're going with. The instructions will be posted again for the next lab, and based on GeoGebra. Basically, that you guys have a rough idea of how this works. All you have to do is, for right now, I changed the value of tau, and before I had a different value of tau, where the curve, this curve doesn't fit this one, okay, because it's maxing almost halfway, and that's not correct. You're going to collect the data, put it in your tables, and basically analyze it based on how you're supposed to analyze to answer all of the questions that are related to it. Any questions about this part? No?
No.
Okay. So we covered these two things, which are very important in terms of the lab, the fillable file, and where to find the fillable file. And this one again, and hopefully you guys before the lab, which is going to be next week, you will have enough time to check GeoGebra and how it works. And then I will be uploading stuff in there. Most of these things that are in GeoGebra actually are they're developed by educators all around the world, and basically what everybody's doing nowadays is taking them and modifying them so that they work for him or her. Okay. Okay, we need to, today, what is it right now? It's 8:30 and we still have a long time to go. And I want to touch bases with this chapter before we basically do applications on it, because that's really what I'm hoping to do. I want to understand, and basically you can answer it in private if you like, that everybody had a chance to go through the entire chapter. And I don't mean just one section of it or two. Or do we still have to cover at least an overall discussion of the entire chapter? Remember, any one of you has the right of veto, basically saying that can we go through the whole thing or we're ready to move on?
I haven't really had a chance to look at it yet.
Okay, very good. Okay, so let me go back into my OneNote. For some reason, OneNote is the one that messed up things today. Let me open a new section in here. Add section. Okay. Section 5 is fine. I'm preparing my OneNote, okay, because I'll have to import some those right-hand rules, because that's really important in terms of the picture. Right-hand rule. Because they will help us understand a lot of these things, and without them, I'll be using a lot my hand, which is not a problem. And I really want you guys to use your own hand too, because it's important that you guys have to have that. Okay. Let me make this one part of the background. Okay, so let me stop sharing GeoGebra and let's get into this thing in here. You guys looking at the right-hand rule again, okay? Yes?
Yeah.
Okay, very good. So this chapter basically talks about magnetism, and draw. Okay, so basically we try to answer the question, because remember guys, when we did electricity, we thought that, okay, why is this thing in here? Let me close this. Okay, basically we said that all we need to discuss the electric field is a point charge, a test charge. Okay, somebody's dog is happy.
Yeah, sorry.
Dog. Okay, listen. We need a 1 coulomb charge to find the electric field. That's all. If you have 1 coulomb charge attached to a mass spring system, and that should tell you whichever way it moves, first of all, that's the direction of the field, how strong it's going to move. It moves this much or that much, depending. If it compresses spring this much or that much, that is the strength of the electric field. Because for 1 coulomb, remember F was equal to Q times E. So that's basically all we needed. So if this number were 1 coulomb, then what the spring measures is actually your electric field. So that was one way of finding the electric field. We said that practically 1 coulomb is too much of a charge, and it's not practical at all to do that. So there is different techniques. Like for example, when we did the lab for it, we found out that you can measure the equipotentials, and the equipotential in one point in here, and then we run the perpendicular to the equipotential area, because the electric field is perpendicular to the equipotential. And at that point, we found the direction of the electric field. The strength of it is still given by basically how strong the descent is. If you go from, let's say, for example, you have 12 volts in here for the equipotential. This equipotential is 12 volts. The one next to it, let's say, for example, is 5 volts. So you go from 12 to 5, that is actually a drop of 7. But if the next to the 5, there is a drop of 4, then there is a weaker magnetic electric field between the 5 and a 4 versus 12 and the 5. So we can find the strength, we can find the actual direction using that lab. But that's electric field. For the magnetic field, it's given actually by the compass. So all we need is a compass. So basically think of it that we're carrying a compass with us, and that compass, whichever the direction of the magnetic field. So it's, in a sense, it's much easier to use this thing in here for the magnetic field than for the electric field, because compass are basically, you can find them everywhere. So where the needle points is the direction of the magnetic field. So that's one way of finding it. Experimentally, the law for it was shown for a point charge moving in a magnetic field is given by this expression. This is kind of nasty expression as compared to the one above it. One above it is just Q times E, and you're done. This one, you have to use the right-hand rule to find the V cross B and then multiply it by Q in order to find where this force is. So this is quite a bit of work. And that is going to be the story, the underlying story for magnetism. Magnetism is a little bit more complicated than the electric field. So you have to have your right-hand rule mastered. Okay, if you don't have that, and don't be shy about it, okay? So you really have to practice V cross B equals to F. If you did that already in vector calculus, or at least in physics 1B, I'm sorry, physics 1B, what am I talking about? Physics 250, this is basically how this thing looks like. The cross product in here is given by a big matrix. So the vectors in 3D, and it has to work in 3D. This cannot work in 2D, because if this is 2D, you cannot do a cross product in 2D at all. So it has to be 3D. And it doesn't work in 4D either, because with 4D, you will have a direction that is completely nonsense that you're going to be dealing with. So this is one of the perks of living in the 3D universe. Actually, the right-hand rule. So how do we know if we meet aliens tomorrow from another version of a different universe that has 4 dimensions? The only way we can tell or communicate between us is actually through the cross product. So the cross product is an important concept in here that you guys really have to master. So again, C is a vector whose components, let's call them C1, C2, and C3, or Cx, Cy, Cz. Same thing with B. That is actually another vector whose components are B1, B2, and B3. And finally, the vector A, also I'm going to write it. By the way, I'm going to post the notes, but you guys really have to take your own notes. So do not rely on my notes and just be there sitting and watching, because that's not going to work. So you really have to take your own notes, because that's how learning happens, okay? And you will have some questions down the road, okay? So when you're taking notes, you might think of something, please do not hesitate to ask it, because it's very important that you guys ask us questions. Okay, on Cartesian coordinate system, because this is dependent on the system that you guys use. On the Cartesian coordinate system, C1, the components of the cross product, is combined with the non-1, basically, of the other one too. So it's A cross B, so it's A2 B3 minus A3 B2. So it's a good idea to write this thing in here and start memorizing it. Basically. This is a cyclic process. That means that if I'm going to find where C2 is, all I have to do is rotate this number. Because now what is it? What is it? The number that is missing in here. The number that is missing in here is 1. So the number is going to be missing in here is 2. So basically, all you have to do again in here is look at this number. C2 is going to be B1 times A3 minus A1 times A3, except I have to flip the sign for C2. So it's going to be A1 times B3 minus B1 times A3, okay? And the last one is going to be straight out, basically. It's like you're doing the matrix, basically, the determinant of a matrix, okay? And the last number is going to be C3, and C3 is straight out. So when I'm doing the last component, it's going to be B1, A2. I'm sorry. Did I mess up the second term? I think I did. Let's look at the second term. It's still A cross B. I wrote them backwards, okay? I should have really kept them in an organized fashion. So the components for C2 are A1 times B2 minus B1 times A2, except I have to flip that side. So this will be a minus and this will be a positive, okay? The terms are correct, except the sign was wrong. This last term is going to be, okay, A2 times B3, A2 times B3 minus A3 times B2. Okay. Have you guys done this in Physics 250?
We've done cross products, but I've not seen this exact method of doing it.
Okay. So the vector C1, C2, and C3, basically, if you want to, you take the determinant. If you're trying to find this vector, you take the I hat, J hat, K hat components, and you start with the first vector of the product, which is A. So this is A1, A2, A3, and then this is B1, B2, and B3. Okay, in terms of components. We're going to have some problems, and we're going to do them at least with this thing in here. So the components for this one is just this product minus this product. So A2B3 minus A3B2, and this is in the I hat direction. In the J hat direction, I have to change the sign in here when I'm doing determinant. I alternate the sign. So this is a positive, positive, this is negative, this is positive again. So it's going to be a minus now A1 times B3 minus A3 times B1. So minus times the whole thing. So I have to flip that order of operation. Here, for the third term, I kept the sign correct. So it's going to be A1 times B2 minus A2 times B1, okay? So when I'm doing this cross product, so basically when I'm doing the J components, I eliminate this whole section and this whole section just to find the J component. Then I do this too. But except for the J hat, because it's the second term, I have to multiply it by a negative sign, okay? This is the difficulty with the cross product. Either you're using the matrix format, it's kind of complicated a little bit, you need some honest work. And it's if you're doing the right-hand rule, also it's still complicated, because with the right-hand rule, basically what you say in this case is the cross product of A crossed with B, which is a vector C. Basically, C in magnitude is easy, is equal to A times B times the sine of the angle between A and B. And since this is a vector, the direction, because we still need the direction of this vector. So the direction of this vector is given by the right-hand rule. So we found its magnitude and we found its direction. That is the right-hand rule. Gives you the direction only. The magnitude is just still A times B times sine of the angle between them. If the angle is 0, the cross product is 0. If the angle is 180 degrees, the cross product is 0, because sine of 180 degrees is still 0. If the angle is 90 degrees, then this is the maximum value. If the angle is negative 90 degrees, then this is a negative number. So that's basically as far as the right-hand rule is concerned. In Cartesian coordinates, you use this matrix representation, okay? I, J, K. In non-Cartesian coordinates, you really have to use also the appropriate coordinates for that. You have to use a transformation between Cartesian coordinates and polar coordinates. It gets complicated. In this course, though, the two basic things that we're going to remember are either the Cartesian coordinate system. In an exam, I'll give you this formula. I'll give you exactly how this formula would look like. I don't want you to memorize these things, but I will not give you the right-hand rule. You need to know that. So you have to know how the right rule works. A times B times sine of the angle between them, and the right-hand rule is your own right-hand rule. It cannot be my own, it cannot be anybody's else. It has to be your own to determine what the direction of the product is going to be. So again, this is Lorentz force. So Mr. Lorentz force, somebody asked a question here, let me see. All right. That is it. Okay, it's done. Anyway, somebody asked the answer to that. I did not see the question. Anyway, so this is part of the what we have seen in that part. So basically, this is how you find the force. And then, of course, we talked about the cyclotron. Cyclotron was developed by Lorentz in the 1930s, I believe. And they were working on an experiment. Basically, this phenomenon was known in electricity, but the technique was refined in, I think, was it Chicago? No. It was in, I don't remember, Yale or one of the big universities, and Princeton or something. Anyway, the point being is you have 2Ds. Those are conducting materials. They're actually hollow regions in here. Okay? So this is how they look like, where particles can enter from one region, and basically this is a hollow zone in here. And there is a magnetic field in here, and there is another D. So this is the 3D version of this D. But the D itself actually was you can look at it from the top. This is how it looks like. The reason why they called it a D, because it has the form of a D. And then also there is another D on the other side, except it's flipped. Okay. Between the two Ds, you have a voltage. You have a power source. Okay. A power source. Think about it. This is a battery. So this is a higher potential. This is a lower potential because of the fact this is connected to If I put a positive charge in here, it's going to move this way, okay? It's going to fall this way. So if I put a proton in there, it's going to fall. Once it enters the magnetic field zone, so there's a magnetic field in here, I'm going to put it down in here. This is my convention. This is actually textbook convention for the direction as perpendicular to a surface that you're drawing. When you see the cross hairs, that means that it's like an arrow moving away from you. When you see the pointy end of the arrow coming to you, that is basically coming out of the surface. So if I'm representing it coming out, this is how I do it. If it's coming in, I do an X usually with a circle around it. So that's going in. So I have a charge moving this way. That's the right-hand rule now. I have a magnetic field going into the surface. Okay, you can practice it right now because it's going to be confusing. You need to find which way the charge will move, will spin. The force is going to be subject to is going to be perpendicular to V. It is V, and perpendicular to also this magnetic field, and it's going to be pointing up. So the force is going to be perpendicular to V, and that is a very big deal because from physics 250, you know that if the force is perpendicular to the velocity, the only motion that is possible in this case is a rotation around some sort of a center. And so basically, it's going to be given by V is perpendicular to B because anything is perpendicular because the velocity is in the surface, is on the screen, okay? And the magnetic field is going into the screen. So anything on the screen is perpendicular to that, okay? So to that magnetic field because the magnetic field is penetrating the screen and the particle is moving on the screen. So the particle velocity is perpendicular to B. Okay, I hope that's clear. Okay, then, oops, I didn't mean for that line to happen. Then I'm interested in trying to find basically we're applying F equals to MA now. F equals to MA, and I dropped the vectors right now because I'm doing this in the centripetal direction because I know this is going to be moving in a circle. Okay, of radius r. And here I have this force is equal to QV times B times sine of 90 degrees. I just argued that the angle must be 90 degrees. Cancel this one and that one, and that's going to be a rotation with a radius that is given by this expression, namely R is equal to mv over QB. That is the cyclotron motion. That is basically a particle is going to be in a circle. Basically, the purpose of the magnetic field is just to push the particle to come back from where it came from. If we switch the polarity, the minute it merges from that magnetic zone, then the particle will fall now in the opposite direction and basically reaches the other region. Now, with Poplawia, the right-hand rule is going to be a little bit different. The particle is moving this way. The magnetic field is coming to the screen. And the particle now, as it comes in, it's going to actually flip on the opposite direction. It moves the other way around. You guys see that? So the purpose of the magnetic field, both of them going into the surface, is that always it's pushing the particle back into this zone. By the time it merges in here, we're going to flip the polarity again of this pattern. So it was pointing earlier, it was this way. We flipped it when it merges out so that this will be positive, this will be negative. And then we flip it again, this will be positive and negative. And every time it comes out of the magnetic region, we're going to flip it so that it goes through. During this time, transition is going to gain velocity. During this time, it's going to gain velocity. Because remember, we use the conservation of energy, if you like. The conservation of energy says that 1/2 of mv final squared, minus 1/2 of mv initial squared is equal to q times v. V is the voltage applied. So this is the energy of the electric field inside the electric field. So every time it's in that region, whatever velocity it merges from, it's going to gain more velocity, and that velocity is going to be proportional to QV. And this process repeats time and time again until it merges out with extreme high velocity. So what they did in here is they made a hole in the opening, and that opening, when the particle comes out from the bottom, it comes out super fast with extreme high velocity. That's an accelerator. Is there any flaw in this argument? I need to know. You guys can think of a reason why this can be a problem? Anybody?
Nothing that I can see.
Yeah, if you're honest, that's probably the correct answer, okay? Because we didn't cover relativity yet. The problem is these particles, there is no limit on their speed. And of course, this is not, there is a limit on the speed with which particles will merge. And actually, that's one problem. The other problem is that because these are charged particles, the faster they move, the more acceleration they will gain, the more they radiate energy. So there is a limitation actually on this experiment. So we will talk about the Betatron later on, and we will see that actually it solves one problem, but it doesn't solve the other. It solves the problem of relativistic speed. It puts a cap on the speed with which the particles can emerge. Of course, you're asking, okay, if I put any voltage in here, technically I can find any if I put any voltage in here, technically I can find any speeds I want. I can go 10 times the speed of light if I want to. That is what the flaw is, really the biggest problem with this argument in here. And it's outside of the scope of this course, of course. And we will understand later on that's not possible, actually. It's not possible to do that. There is always a limitation. And the minute the speeds become too high, you have to do relativity corrections. And we'll probably have to revisit this very same problem later on when we do the physics 252, okay, and find how we fix that. And in the case of the Betatron, actually it solves that problem from the front, but doesn't solve the other problem, and that's the radiation. And actually that's a practical limitation, and that's because particles, as they move, gain more and more speed, they start to radiate more and more energy, and that's how basically they cannot reach the speed of light. Okay, I have a question here. So if the magnetic field is negative, the charge is repelled. I don't understand this question honestly, but basically, if the magnetic field is negative, what do you mean? If it's coming up to the surface, the whole experiment will be reversed. That's all. Okay, it's a good question actually. I mean, because you always have to think, oh man, my screen is not responding again. Okay. Hopefully it's not going to be a... Okay, anyway, if the magnetic field was not going onto the surface, but was coming out of the surface, then, and the particle was moving this way, remember we took the charges to be positive, okay? So it's moving this way, and the magnetic field is coming out of it, out of the surface, not into the surface, then the whole process will be basically moving in the clockwise, and instead of being counterclockwise, that's all. So this experiment will work both for positive charge and negative charge, because instead of reversing the sign of the, let me stop the sharing, hopefully, because this thing is not responding to me. Okay, I think for some reason this whole thing is not responding. Create a new section in here. Okay. I have so many things going on, so probably if I close this one in here. Cancel, I don't know what I did. No, don't save. Okay. Anyway, the point being in here is that that's a good question, actually. Always think in terms of what might happen if you do this and that, and always try to remember the right-hand rule. And that's a question I should have asked for you guys in terms of that. So that's basically how the Lorentz force works for us in here. Okay. Let's see if the other one is still responding. Okay, good. Now it's responding. Okay. Because it's important that this responds for us in here because we have a lot of content in it. So that part I hope is clear in terms of, I know we did the velocity selector, and the velocity selector basically is a combination of two things, the electric field and the magnetic field, and that you have up and first, okay? So you have two plates basically. This is a velocity selector, with a positive place in here and negative place in here. If it doesn't work, just reverse the polarity and you're going to be fine. Okay. So, and you have a magnetic field that I'm going to take inward. The whole region is inside a magnetic, not just this region. Okay. Actually, we don't need it in here. We want it in here. We want the magnetic field in this region. Okay. And you have a charge that is coming in here, Q. I'm going to take it positive and see what's going to happen. Because it's going to be subject to the electrostatic force, and the electrostatic force, if you guys remember, it's Q times E, that's all. So it's going to be bent inward, downward. So it's going to be, for the electric field, there's going to be Q times E, this is a vector, and the electric field is pointing down. So the force is going to be down because Q is positive. So the particle will bend down, okay? But if I use the right-hand rule, V is this way. The magnetic field is inward, is coming to the surface. This charge will be bent upward per the magnetostatic force, QV cross B. Okay? Whereas the particles that are moving super slow, because this force now will be less, will be bent downward. The particles will come in here and fall into the bottom, because this force is not big enough to balance the electrostatic force. The electrostatic force will win and move them down. Whereas the particles that are moving super fast, they will bend upward and they will end up in there, because the magnetostatic force will win and the particles will end in the positive place. The particles that just have the right force, the right velocity, I should say, they will be unaffected. They will come straight through and through, because these two forces cancel each other. And when they do, this force will not be subject to any net force, because the sum of the forces is equal to 0. In other words, E plus V cross B equals to 0. If that's the case, these particles will be unimpeded, basically as if there is no electric or magnetic field for them. So these particles that have the right velocity will come straight through and through. That's why we call this one a velocity selector, because if I do the cross product, E is pointing down, so I'm going to take the sign for it to be down. So E is down, I'm going to take it in that direction. V is this way, the magnetic field is inward, so the angle between them is 90 degrees, so sine of 90 degrees is 1, and the force is pointing upward, so it's V times V equals to 0, okay? So I use the right-hand rule and solved my problem. I could have used the cross product, and I also did the same thing. So if you guys want to, you can practice this one with the cross product. Very easy to do with the cross product. Okay, I'm going to take the x direction, y direction, and z direction. I'm going to assume this is the x direction. That's the direction of the velocity. So I hat. So this is v. The b is in the y direction. So I'm going to assume that b is in the y direction. So this is 0, 0 as far as j hat and k hat. And this is, of course, the magnetic field is actually in the y direction. So this is my x direction. This is my y direction. And this product in here, in the I hat direction, I have 0 times 0 minus 0 times the b. That is 0. So it's going to be 0 I hat. I have minus v times b. V times 0, which is 0. So v times 0 is 0, and 0 times 0 is 0. So it's going to be minus 0 times j, plus in the k hat direction, v times b minus 0. So it's very easy to do it also with the coordinates. So again, v this way in the x direction, the magnetic field is in the y direction, going in. The force is going to be in the positive k hat direction. I just took the positive k hat direction pointing upward, which means that the electric field is actually pointing negative because it's going down. So this is positive and this is negative. It's still the same value for the velocity. You guys see that? So the electric field is pointing down. Remember, it's a negative value, and v cross b is up. So this value is going to be positive, and the velocity with which these particles will emerge is actually given by v equals to, what is it, e over b. It's still the same velocity. So this is what we call a velocity selector. There's another thing that is actually used, and I didn't talk about it in my notes, and hopefully you guys have read about it, and that is the mass spectrometer. Mass spectrometer actually is when you have particles in here of the same charge, the same material. For example, you ionize carbon atoms and you remove 3 electrons from them, and now they are positively charged, or you add to them 1 electron, or what is it? Yeah, you add to them 1 electron or something like that, and they become positively charged. But you have carbon 12 and you have carbon 14, and you have different isotopes in here. One of them is heavier than the other, okay? You run them through velocity selector, they both will come with the same speed. It doesn't matter, because the velocity selector doesn't care about the mass. So you run them through this device first as they emerge. You accelerate them if you want to through an acceleration device from the first one, cyclotron if you like. Now they come up with probably different velocities depending on the state. You run them through the velocity selector, and now they merge off of this point in here with the same velocity. So now they are coming with the same velocity, but remember they have different masses because they have different isotopes. So the particles are positive. Let's assume that they are positively charged, and you put them in a region when there is a magnetic field. We're going to point it inward in here. In other words, there is a north pole on this side of my screen and a south pole on the other side of my screen. Basically, take a horseshoe magnet, if you like, and put it this way. Okay. So this reason is there is a magnetic field pointing into the surface. So the particles, they emerge like this one at the velocity, and now so this is the velocity. Magnetic field is inward into the surface. So in this case, the force is going to be bending them this way. But of course, some of them will land in here and some of them will land in here actually. Okay, do you guys see the difference? And why is that? Because from the first thing that we did in the beginning was the cyclotron motion. The radius with which they bend depends on the mass. It's ND depends on the momentum actually of the particles, and the momentum of the velocity, they have the masses. Okay, so the radii will depend on the mass, NV over QB. They have the same charge, they have the same V, they're in the same magnetic field, but they have different masses. You guys understand that they will land in 2 different points if I have only 2 isotopes? Yes? Yes or no? Is everybody here, or do you guys left your microphones and went somewhere else to have some breakfast or something?
I'm still here.
Okay, that's funny.
Yes, I see what you're saying.
Okay, good. Because anyway, the point I'm trying to say in here is that with different masses, the lighter material will end in here, will end in 1 point. So if this is carbon 12, for example, and this is carbon 14, if I make sure that they're both ionized the same way, basically, and they have different masses because they have a higher number of protons. So this device is called actually a mass spectrometer. Mass spectrometer is, can you distinguish between different masses of different materials? And you do this. You run them through a velocity selector, and they go through and they bend in different areas. I know I didn't talk about some of these things in the notes, but I'm hoping that you guys are reading through these things and you understand them. Okay, I hope that this makes sense in terms of the general idea. Then we talked about the magnetic flux. Magnetic flux is an important concept that is going to be very important for us in terms of this chapter. So the flux, we defined it for the electric field, and now we're defining it for the magnetic field in the same fashion, except that in the electric field I have E, here I have B times an area, and this is called calculated over any kind of area. You have one of the homework problems deals with this very same question. You're supposed to calculate the magnetic flux for that for different surfaces. Did you guys have a chance to go through the homework? So basically the homework problem was like this. You have a surface. I think it extends like this one. You have a magnetic field pointing in this direction, and you're supposed to calculate its flux through different surfaces. One of the surfaces is this one, and one of the surfaces, I think it's the top one or something, and the last surface was this surface, and the final surface was actually the entire surface, the whole surface covering this whole piece of what looks like cheese to me. Do you guys have a chance to look at the problems for the homework?
I have not looked at them yet.
Okay. Do you guys want to do this problem? Because that's part of the things that we're supposed to be doing. I see some questions in here. Okay. Somebody said yes. Did you mean for the homework problem to do it now, or did you see it? Chad. Oh, okay. So you guys want to discuss this problem in here to see how this works? This is an application. And I still want you guys to submit this problem, okay? Because I really want you guys to have a full understanding of this thing.
Yeah, let's look at it.
Okay. I have got, and Dr. Adam shared a lot of resources with me the other day, including this great thing. Okay, so this is the problem, okay? Problem, what is it, 14 from the homework? Problem 14 from the homework says that basically what you have in here, the magnetic field in a certain region is 0.128 Tesla. What is the, so B, the magnitude of B is 0.128 Tesla. So that's the strength of the magnetic field. And what is the file itself? And it's in the positive Z direction. And they gave you the areas. The areas are 30 by 30 and 40 and 50. Okay, so let me get these numbers in here. Centimeters, of course. Everything is in centimeters. So this is not right here. Okay. So this side is 30 centimeters. This side is 30 centimeters. All of these units are in centimeters. Okay. This is 40 centimeters. And this side in here is 50 centimeters. And they want to find, first of all, they labeled these things in here in the homework problem. A, B, C, D, this surface. So this is A, this is B. I think, is it the center C, C, and D? So there is a surface. You guys see the picture or not, or should I redraw this picture because it's kind of a. I want you guys to draw it too while I'm doing it. Okay. So this is the x-axis, the y-axis, and the z-axis. Okay. This is one surface. And this surface is in between these two axes, where this is the direction of B. The main thing in here is the direction of B. This is B. Okay. And this is one surface. I'm going to go back into that surface in here, its dimensions. I think its length is 40 centimeters and its height is 30 centimeters. So this is 40 and this is 30. Okay. And how much flux do you think, guys, should be? And I want an answer right now from everybody who's present in here. Okay. It doesn't matter if you agree or don't agree, but I want to guess numbers in here. Somebody says 0. Adam thinks it's 0. Do you guys agree with him, or are you talking nonsense again? Do you think some of this habits will go now?
Why would it be 0?
Okay, can you answer that, Aaron?
Just out of curiosity.
Can you help us, Aaron?
It's because I think that like for the K direction and I direction, that product would be like it would be 0, so it would make the whole flux 0.
Okay, why did you pick up the I direction? The I direction, you mean, let me draw it in here. You mean this is the I hat direction, yes? And this is the J hat, and this is the K hat. The magnetic field is in the K hat direction, yes?
Yeah.
Right.
So, and the I hat
And
is
the
the
area.
okay.
The,
The area is in the I hat direction. Do you see that?
yeah.
Okay. Everybody else. The
Yep.
area in this case of this surface in here is pointing in the X direction. Why is it so? Because any flat surface in here, let me see what is that. Okay, this is a flat surface. The area is actually this one. It's a vector pointing normal to the area. It's not a vector along the X or the Y, I mean, this axis or that axis, it's perpendicular to it. Since this area is along the Y and Z direction, that is actually in the YZ plane, it points in the X direction no matter what. And because the flux involves the dot product of the vector field, I mean, in here, because B is uniform, so we're going to take it out of the integral, and all we left with is actually the flux is going to be just simply the product of these two vectors. So phi for this part in here is simply B times A, okay, in dot product. Because B is in the Z direction and A is in the X direction, the flux here is 0 because of cosine of 90 degrees.
Right.
Does everybody agree?
Because they're perpendicular, the cross product is 0.
Perpendicular cross product is 0 under the story, so this is no problem.
Okay.
Okay, so let's see what the next question was. What is this? Can I get this thing out of the way? This Zoom thing is becoming in the way. What is A, B, C, D? What is the magnetic flux across the surface BEFC? In BEFC, BEFC. It's in this surface now. I want the flux in this surface of each side being 30 centimeters. So this is 30, and that bottom one is 30. So this is the 90 or 900 centimeter squared area. Okay, I have to convert things to 0.09. Basically, the magnitude of the area is going to be 0.3 times 0.3, and that's 0.09 meters squared. So that's the magnitude of this area. Now, does anybody have any idea? First of all, the sign of the cross product in here, of the dot product, I'm sorry, because we're looking at the flux. Is it going to be positive or negative? And or is it going to be 0? Ask yourself, the area now, at least physically, it's in the plane perpendicular to the X and Y direction. And what is that direction that is perpendicular to the X and Y?
The Z direction.
Z direction, okay? So the area is in the Z direction and the magnetic field is in the Z direction. So can I say it's 0 now? Is it going to be 0, do you guys think?
I don't think so.
Okay, it's going to be a number, good, because now they are not perpendicular. Actually, they have the same K hat somewhere, but we're kind of worried. Somebody thinks, actually, Aaron thinks it's negative. Can you tell me why it's negative, Aaron? He thinks the area is pointing in the negative K hat direction because we know definitely the magnetic field is pointing in a positive direction. So it's going to be basically what he's saying in here, if I can understand it, is the flux in this area now. This is phi 1, okay, the one that we found is equal to 0. Phi 2 now is going to be negative 0.18 Tesla, 0.128, I'm sorry, Tesla, times 0.009 meters squared. And he's saying it's negative 19 because although this magnetic field is positive, the area actually is going from J to I. So it's going clockwise, okay? And when you go clockwise, That's another rule, I didn't mention it, and that is the screwdriver rule. So when you go follow the clock, in this case, that's also another way of finding the area. So the area is going to always follow basically which way you're going to curl around it. So if we go from J to I, the area actually is pointing in the negative direction. And that's why the area in magnitude is 0.09, whereas this direction is actually in the negative direction. Or if you want to, it's in the negative k hat direction, and k hat times k hat is 1, but the negative number will make it negative. Does everybody agree? Is it actually correct? It's a negative number? Yes?
Yeah.
Okay. The question that is, what is the magnetic, so we did, what is the magnetic flux across the surface AEFD? Oh, that's going to be a little bit of work in here. So we have to do some honest work now. Because this area now, where is my, this area now? This is 50 centimeters. And this is 30 centimeters. So the area, and it matters which way they tell you to read it, okay? So the question says, let me go through it again. The question says A, which is the top, going to E, and then F and D. So the way they are describing it is going this way, going basically from here, from this point in here, that is A, going to this point in here, I don't know what they labeled this and that, but going this way, and coming down and going back and coming back to the point in here. So the magnetic flux now matters. If you're going in that orientation, again, you're going this way and coming down, the area actually is pointing inward. If you're going from A down to the bottom, let me make sure I read it correctly because I don't want to get the wrong sign either. A to E. Yeah, if we're going from in that direction, the way I showed it, it's going to be a negative number also because it's going to have two components actually. And the magnitude, you can find it. And the direction you're going to find, it's going to be actually it's going to be just a scalar number. What am I talking about? I thought I'm doing cross product again. So it's only going to be a number. It's positive or negative, so that's a flux. So phi 3 now. I need to find the direction of this vector that is perpendicular to this side. Pointing inward. Do you guys see that? Yes?
Yeah, I get you.
So we need to find the coordinates of this point in space and the coordinates of this point in space and basically form the perpendicular to it. Once we form it, that is going to be the direction of this, and it's also perpendicular to this vector too. The direction is given by this coordinate. Once we do that, we can form the cross product. I prefer using the Cartesian coordinates, and if you want to, you can find the area, which is 50 times 30, and try to find the orientation of this vector that is perpendicular with respect to the k hat direction. The B is in the k hat direction. We don't have a problem with this one. We need to find this direction in here. Once we find it, we're in business. You guys understand? I'm going to leave this to you guys to do it. It's not hard. Just trying to play with geometry, that's all. Once you find that answer, that's basically the work that needs some work in here in terms of some honest work. You guys understand in here what we're doing? The area, the magnitude of the area is what? 50 times 0.5 times 0.3, which is what? 0.15 cubic meter, square meter, I'm sorry, that's the area. So we found this magnitude. We know the magnitude of the electric field, or the magnetic field. All we need is actually the angle, cosine of the angle between them. And once we find that, then we're in business. Okay? Yes? You guys can do that. Geometry. The last question, which is the magnetic flux through the entire surface. That should be easy enough to do. Through everything, all of the surfaces added together, including the bottom one. How much is that going to be? Why? I'm saying it's 0. We don't need to do any calculation. That's it.
Because of Gauss's law?
Gauss's law for the case of magnetism states that the flux over any closed surface of the magnetic field is 0. And why is that? Because there are
Dot product is 0 or something.
no monopoles. You cannot isolate the North Pole by itself and the South Pole by itself. End of the story. No monopoles. That's an important law, okay? So the last question was to find the magnetic flux through all the entire rear closed surface. That's an easy, even I can do that. Because it's, you're going through a closed surface, and once you go through a closed surface, basically you have no magnetic flux. Because the magnetic field penetrates this region from somewhere and will ultimately come out from the other side. And when you tally all of these magnetic fluxes, you're going to find 0. Actually, if you calculate it through all of the other surfaces, granted that some of them will give you 0, at least one of them will give you 0. That's the first one, because E and the area are perpendicular. The others, they will give you finite numbers. The top one will give you 0. The bottom one will give you 0. Can we agree that it will be the same as this number then? Except it's going to be positive for the other one? Yes, do you guys see what's going on? I mean, at least using Gauss's law, we can find this answer without even having to do it, phi3, the flux through this complicated surface. It must be the same number as this one. In Weber, of course, you have to make sure that. Because this surface is 0. The bottom one, the surface is going to be in the y direction. The top one, the one is going to be in the negative y direction. So those are going to be 0. Somebody writing in here? Yes?
What happened?
Where you can write in there?
Yeah, somebody was writing in there. That's good, actually. Who did?
Oh, you can see that?
Yeah.
I just saw that and I started messing around.
Okay, good. Apparently, when I share my screen, hopefully I'm not uploading viruses on my screen.
No,
Okay.
at the top of the where it says you are viewing this person's screen, you can view options and annotate.
Okay, Aaron requesting remote control of your screen. No, do you want to really? Okay, I'm gonna allow you. Go ahead. Okay, Aaron now is taking charge. Okay, that's
Aaron,
good.
what are
Actually,
you doing?
Okay, so the point in here that we have discussed so far in this class is the Gauss's law, which is a very important concept. Later on, we're going to need big time when we do chapter 30, and chapter 29 actually will touch base with it too. So I want you really to have understanding of the flux. This is not going to go away. So this is one of the problems that we have discussed. Okay. Another thing that we have discussed in this chapter, what else did we discuss in this chapter? Oh, the work. That's an important tool. That's because we will be building motors, and all the questions is, okay, we need magnetism to build a motor. And I'm thinking actually to have that one of your projects to be working on. If you go on YouTube, how to build a motor, you should be able to see it. I went to campus the other day, looked for magnets. I couldn't find any magnets that are basically that you can borrow. So I want to know, and probably I will send a survey, and hopefully you guys can answer it individually. I want to know if you guys can do that or not, because although we are doing remote instruction and we're going to do lab online and things like kind of a little bit not too perfect in terms of physics hands-on. So I want you guys to be able to somehow do some projects, and I'm thinking seriously about the motor so that you can build your own motor. And I will demo one, basically build one, and you guys can build your own motors. So the question is this: how in the world we're going to use magnets to make things move And for you to make something move, you need something to do work. But I argued in the lecture that there is the magnetic field does no work. W equals to 0. And it's very simple. Why is that? Because of the cross product again. So when you calculate the power, or actually when you calculate the work of a force in here, it's force times displacement. That's what it is. Okay? That's what work is. So an elemental work for a charge moving in a magnetic field is going to be given by this expression. This is from physics 250. This is QV crossed with the B, and the whole thing is times dr. This is the last part is a dot product. The first part is a vector product. So normally what you do in this case is you divide it by dt and you multiply by dt. This is stupid what I just said. It's not possible because d is not division. D is an operation. So usually what you do in physics, in practice at least, this is what you define work. You don't define it in this differential form. You're going to define it in a finite value. You allow delta time t that passes. The particle will move a finite displacement delta r, and then you find the increment work that the force does during this displacement. Then you say, you know what? I'm going to divide. Then you can divide because you have a finite quantity. You can divide by delta r over the span of time that lasts times delta t. So this is how you do it, really. This expression on top of it doesn't make any sense. This one makes sense. So then you say, you know what? I am willing to let delta t now go to 0. If you do that, then the limit of this expression becomes delta w, or the change, the infinitesimal increment in the work due to this thing is going to be the ratio of delta r over delta t and the limit when delta t goes to 0. That's v times the infinitesimal displacement or the infinitesimal time. As a matter of fact, dw over dt is the power. Okay. So if you're finding that expression, then you say, how much work is that? Well, qv crossed with v times v times dt. This expression is 0 because no matter what happens, v cross v is perpendicular to v no matter what, because v cross v is perpendicular both to v and b. That is the properties of a cross product. In particular, of that perpendicularity is the fact that it's perpendicular to v. And the fact that it's perpendicular to v dotted again with v will involve a cosine of 90 degrees no matter what. So this thing in here is going to be 0. As a general rule for the cross product is, if you take any vector and cross it with anybody else in the universe, it doesn't matter what that vector is, and dot it with the same vector, it's going to be 0. That's part of the properties of the cross product. This is exactly what happened in the case of computing power, or in the case of finding the work, that the magnetic field does no work no matter what. It doesn't have, it can be any day of the week. That's a lazy thing. Okay. So the question, and it's a very legitimate question, is how in the world can we build a motor? Why do we need magnets if they don't do no work? Okay. We'll have this discussion later on, and it turns out the answer to it is that yes, the magnetic field does not do no work, but facilitates work. It helps work to be done. That's basically the answer to it. So that's why we need them actually to build motors. Okay. So that's one of the things that is essential for this concept of magnetism. And now there is no motor in the universe, at least electrical motors, that doesn't have magnets in there, including the Teslas, including those fancy cars, including the Priuses and all of this electrical moving things. So that's in terms of work, and it's an important idea in here. What else did we discuss in this chapter that I'm forgetting right now? It seems like we're wrapping it up quickly. We still have no. What else did we discuss? Anybody else? Oh, it's a big deal. The biggest part of it too. I mean, this stuff is by far very, very important. But the force basically on a wire. This is this is basically a wire, okay? And it's inside the magnetic field. So this is B. And there is a current in here running through it. Obviously, you're asking, how in the world am I going to have a current through an open wire like this one? If you just think about it as a very, very long wire, okay? And we just took a snap picture of it just for this portion, okay? We're doing physics, we're not doing math. And I really want you guys to think in terms of how am I going to do this in practice? You guys understand that? This is still a physics class. This is not a math class. And there's so many theoretical things in there that discuss things in kind of abstract fashion that loses track of what you're doing. So this is not the whole picture. So this wire extends to some points in here, or think of it even a small wire. Okay, do I have any wire in here? This is not even a conducting wire. This is my camera wire. Okay, so this is a wire. So if I take this wire in here and think of this portion only of the wire, I'm not interested in what's going on toward the other edges or something. Just interested in this region. And if I bring a magnet next to it in here, I should see some effect. That's basically what this means, okay? Well, it turns out, after lengthy derivation, that this wire is going to be subject to a magnetic force, and that magnetic force is given by F equals to I times L crossed with B, where L is this length in here, okay? And the direction of L is in the direction of I, okay? This is derived directly actually from Lorentz force, and this is basically how this wire is going to behave. So in my picture in here, I have the L is pointing this way, B is going that way, and the force is going to be perpendicular to both the wire and B. So this angle is a 90-degree angle, and this angle also is a 90-degree angle, and this is the direction of this force. So the wire actually will bend because of the magnetic field, as long as there is a current running through it. This has a lot of applications actually. This is, including what is those devices, the ones that measure currents, galvanometers, and some sensitive equipment for measuring currents. This has a lot of applications in real life. So we have all kinds of situations in there. Now, down the road, there will be a big discussion in terms of how this impacts the how magnetism is formed, which is actually the next chapter, chapter 28, and we will have a discussion into how magnetism is formed, and you will see that. I just remember the person that I didn't see in the attendance today, and that person is not here. There's no one I'm talking about. Actually, we lost some people too. No.
But I went to the bathroom right now.
No, I meant there is what's his name? The name escaped me right now. Winter. Yeah, Winter is not here. Yeah. Anyway, because usually Winter has some very good questions also too. So that's one thing that we have to do. And did we have anything in here that I missed in that chapter toward the end? I mean, we didn't talk about the Hall effect, and the Hall effect I usually don't test on it, honestly, because treating it in classical mechanics is kind of not fair, because basically what you have in here, you have a current running through a wire. So you have a current in here, okay? And if you put the wire inside a magnet, actually magnet, not an electrical field or anything like that. It doesn't matter which way it's pointing. The charges now start to move. So they're moving this way inside the field. So actually the charges, the positive charges will find themselves moving closer to the top portion of this wire than to the bottom portion of the wire. Now this can be, will create basically a net voltage in here, okay? So the positive charge, actually, because they're the electrons that are doing the action motion, so they will move to the bottom, and you will have the same net effect basically. that you will have a voltage that is created in across the. I'm thinking in terms of blood blood flow or all kinds of flows. The Q is actually there to determine all kinds of properties. It's not really fair to treat it in classical mechanics because this is a quantum effect, honestly, and the quantum it's really a whole. The whole effect itself is quantum, and I don't like the treatment in classical mechanics. It's a very rudimentary approach to it. Okay. What else do we miss in this chapter in here? I'm kind of puzzled right now. Did I cover everything? Do you guys think that we covered everything, or we still have some stuff that we need to? Oh, that's another thing also, and that is the motors. Since we mentioned the motors, and that is the loop. Okay. We covered the loop. Basically, this is basically what you have. Again, this is not practical. Basically, you have a conductor that you loop it around, and the current will go around and around in it. Usually, in practice, what you do in this case is you have actually a. This is how this looks like. And this is how you're going to build it, actually. Although you don't have to have it square. Actually, square is not going to work very well. So you have to have some sort of a circular shape, okay? So you have a wire that you run it through several times. So in practice, this is how this looks like. Make sure that it's insulated, okay? And then you come in here and you shave it, actually, because you're going to connect it to some power source in here. Otherwise, when the wire touches, then you will have a short circuit in there. So the more loops you make, the stronger actually the mu is going to be. Remember, the mu, the magnetic dipole in this case is IA. But if you have only one of them, you have only one IA in there. A is the area. The magnitude of this magnetic moment in this case is that this area times the current in it. And this is similar to when we did the electrical dipole. When we did the electrical dipole, if you guys remember, it was a vector given by this expression, T equals to Q times the distance. 2A was actually the distance, not just A. A was half the distance. That's why I multiplied by 2A, between the negative charge and the positive charge, times some direction, which turned out to be, we took it always, going from the negative charge to the positive charge to be the I hat direction, the x-axis. Doesn't have to be. The water molecule can be oriented whichever way it wants to, so it doesn't have to be. And that's where P points always from the negative charge, from basically where the position of the two hydrogen atoms that are going to be, because the electrons will move closer to the oxygen atom, to where the oxygen atom is. So that's basically where the dipole would need to be pointing, and that is P. And in this case, magnetic dipole turned out to be, by basically definition, when we worked out the algebra, to be IA. Well, which direction is going to be? It's going to be in the direction of A, again, given by the right-hand rule. How am I going to current is? So in this case, the current is going counterclockwise, so the area is coming out. So this is where A is. If the current was going in the opposite direction, the moment will point in the opposite direction, that's all. So you need to follow where the direction of the current is. So if I'm going to draw the wire again, and for some reason I have the current going clockwise in it, then the area will be pointing down. In other words, the dipole moment, mu, will be down also, because it's basically the current. Where is this thing? Okay, for some reason now my screen is not responding again. Okay, I can only type now. I can't try it by hand. Anyway, so mu, oh man. Okay, this thing stopped working now again. I'm sorry, guys, okay? Does anybody have any questions so far? Because till I figure out my screen in here.
If it was clockwise, wouldn't the magnetic field be upwards?
The magnetic field is an external magnetic field. It's not a, it's basically you take bar magnet and you put it, that's it. Let me, if you can have my screen back again. So basically, the bar magnet, we're talking about magnets because that's basically what we do so far. We'll talk about electromagnets later on as part of the course. But basically, you take a bar magnet, and let's say this is the North Pole, and the field lines will start going this way, okay? So this is B. So this you have no control over. The way you change the polarity in there, that is your job in here, okay? So if the positive pole is in here, the battery, you can change it in such a way that this is basically the positive, and this is the negative, and this is where the current is flowing, okay? Obviously, if you do it this way in practice, you're going to burn something. You're going to start smelling things. If this wire is superconducting, it has a very low resistance. But when you run it for several times, you can find this resistance. Actually, remember the resistance of a conductor is still given by rho times what? L over A, okay? So in the practice, when you get to wire, you're going to measure its length first, how long it is. And you're going to go with calipers if you have access to them. If not, you're going to find that the gauge, actually, every wire that you go and buy has a gauge, and the gauge has specific meaning in terms of the cross section, how thick it is, okay? So you have A, basically, pi times d squared over 4. That's the area. And then you have the length, which you can measure. That's L. And depending on what material it is, if it's copper, you can go and look up how much the resistivity of copper it is. And that's most of the time what they have in the market is copper. Unless you're going to go and spend a lot of money on some sort of a silver wire, or even more so on a gold wire. And don't do that, okay? Okay, so we have this wire in here. It has specific length. It has specific cross section. And it has specific material, so you know its conductivity. If it's iron, if it's made out of iron, then it has a different conductivity, and it has a different. The problem with the iron is, well, the problem with any wire actually is make sure that it's shielded. Most of the ones that if you go to Home Depot, you'll find them that they have already this very, very thin cover to protect them, basically. Otherwise, you'll have electricity running all over the place. Those are the ones we use. Because when you wrap them around, basically several times, you're going to be able to, you're not going to be worried about them touching, and then you'll have a short circuit somewhere, okay? So the area now for that is going to be, you have to make sure that this drawing is bad, okay? Make sure that they're very close from one another, otherwise you'll have different areas. This is the radius for the inner ones, and this is the radius for the outer ones. And you're going to use that for your expression of the area, because they took them circular. Then you're going to find how much pi times r squared in that case. That's going to be the actual magnitude of the area. And mu would depend on the current. So if you use a 3-volt battery, for example, a 1.4 battery, 1.5 battery that you can get from Home Depot or Walmart if you wish, that's going to be your battery source in here. What I usually use is paper clips to have the wire sit on it. So I need to have the resistivity also of the paper clip, which is made out of usually iron compound. So you can find you find the cross section of the paper clip, and then now you have the whole thing is resting on paper clips, and make sure you shave the ends of them. Once they are shaved, there is a connection for the current to flow through the wire and go through several times the wire. And basically, if it's coming this way, it goes several times and comes from the other end, goes through the other paper clip and close the circuit on the battery. And now you have a current running through this one. How much current it is very easy to find. Once you find the resistivity of the copper, the resistance of the copper formula, using the same formula also you find the resistance for the paper clips, and there are 2 of them. Then hey, you have the overall resistance, and the overall resistance is just the sum of the 3 resistances, so that's R equivalent, because they're all in series, is R1 plus R2 plus R3. I meant this for 2 paper clips, and this one for the copper portion of it. And the current, now you have the current. How much current is running through the circuit? I. which is if you get a 1.5 volt battery divided by this R equivalent, this is Ohm's law. Now we have the current and we have the area. So we have the mu. Now we have to find the expression for the torque basically. And the torque is given by the expression tau is equal to, it's a cross product again of mu crossed with B. You see how many cross products already involved? In A, there is a cross product already. In B, there is also a cross product somewhere, and then you will see it in the row. And now the tau itself is another cross product. So the cross product is running is everywhere in this place. And you really have to pay attention to your signs. Okay. The good thing about it is the right-hand rule is very easy to use. If you're using with the components, it's a lengthy calculation, but it should be also doable. Okay. Now the energy turned out, this is very, very similar to the electrical dipole. And I remember I told you guys that for the dipole, P cross E was equal to the tau. So this is the electrical dipole, two charges, the same charge, and they have opposite signs. So somebody asked me in lecture, what happens if I have two charges of the same magnitude but the opposite signs? That's not the electrical dipole. That's not what we're talking about. That's not true for this case. Or if they have different values, that's also not the case in here. Okay? It's going to have different algebra, which is not what we talk about when we're doing electrical dipoles. Electrical dipoles usually are neutral, so they have the same charge and opposite charge. Okay, and that's what we use for antennas. Actually, antennas are called dipole antennas because they are actually made up of this format. So that's in telecommunications. Later on, we'll talk about that a little more. So that's basically used actually antennas trying to send and receive signals. The magnetic dipole in here, which is by nature, it's a dipole. You cannot have a north pole by itself and south pole by itself, no matter what you do. So it's a dipole. It comes always in two different things. And that's its moment, mu is equal to IA in terms of algebra. That is an important formula in here to remember. And this is the torque in this case, okay? Once you have the torque, you can find the energy. And the energy, again, is basically, and that's the question probably Aaron was asking earlier, is, okay, I have a dipole now. If I don't have any magnet, the dipole doesn't do anything, basically. That's what the motor is. If the magnet is sitting by itself, and there is no problem. You can have a wire laying around with a current running through it, there is no problem whatsoever, okay? That's not going to have any problem whatsoever. But if you bring a magnet next to it, and if the magnet and the mu are not parallel, they want to be parallel. That's basically what the energy is. So there is an excess of energy, and that energy is given by this expression. Oh, what am I talking about? Energy is a scalar. Okay, so the energy U is given by minus tau dotted with B. I'm sorry, mu times. What am I writing in here? This is nonsense. Okay, you guys need to correct me. We're not in lecture, but you really need to be screaming and shouting that this is nonsense. Minus a mu dotted with B. That is energy. Okay, that's how much energy. In other words, if they are anti-parallel to one another, let's say, for example, this is mu, and this is B. Negative times negative, because this number is going to be negative. So this whole thing is going to be a positive number. Do you guys see that? That if they are anti-parallel to one another, because the dot product is negative. And then in negative, they make them positive. So there is an excess amount of energy, and this two will flip actually in such a way at the end they will be parallel, so that the energy is as small as possible. Okay, so the stable configuration is this. So this is B and this is mu. So in this case, I took, it doesn't have to be this way, but I took mu to be bigger than B. It doesn't matter. So this is a stable. The energy is the lowest possible energy that you can have when both of them are parallel. When they are not parallel, they want to be as parallel. Okay, they want to lower the energy. This is the maximum energy, and the maximum energy happens when both of them are anti-parallel, and it's equal to mu b in magnitude. The minimum energy is equal to, this is where the happy place they need to be, minus mu times b. So the difference, the gap in energy between the highest energy possible and the lowest energy possible, delta U is equal to twice this number. Okay, that's the maximum energy you're going to get from a given magnet with a given value of B and with a given wire configuration with the current running through it. That's the maximum energy you're going to get. It's 2 times mu times B with no cosine or nothing. In any other configuration where this is a mu, for example, and this is B, this is the angle between them is theta, then there is an energy in this case, and that energy is going to be equal to, which is somewhere in between mu with a negative sign times B times sine, cosine of that angle between them, cosine of theta. Okay, so there is a region in here between the lowest and the highest energy possible. This discussion is valid for both the electrical dipole and the magnetic dipole. Both of them have the same discussion. In terms of energy as a function of theta, I'm going to take a theta in here anywhere from negative, what is it, 180 degrees to a positive 180 degrees, running through 0. The energy is max here, and it's min here, okay? And it goes through like this. It vanishes when theta is 90 degrees or negative 90 degrees. And it's its lowest possible value, which is negative mu b. And it's its highest point value, it's mu b in here. You take a dipole and move it out of this region, out of the least possible value, it's going to come back. It's like a plate, okay? Like your plate at home. There is a point on the plate where everything is the lowest possible on that plate. If you take a marble, for example, and move it out of that lowest point, the marble would want to come back to the lowest possible point in there. So this point in here is called the stable. Stable. Because tau is equal to 0 here. Why is tau equal to 0? It's because theta is equal to 0. When theta is equal to 0, tau number is equal to mu times b times sine of 0, which is, so the sum of the torques actually cancels. And the energy is at lowest possible value in here. And so is tau over here also is equal to 0, so there is no torque in here either, because you have 180 degrees. Sine of 180 degrees is also 0. But this is not a stable, this is an unstable equilibrium. Did you do that in physics 250? Did you guys do unstable and stable equilibrium?
Yeah, we did like a brief one on the graph.
Yeah.
Yeah. We just had a diagram where you had to list like what was like the most stable.
Yeah. So this is the stable. This is permanent. If the magnet and the torque, I mean the dipole are parallel to one another, it's stable. If they are completely opposite to one another, that's actually stable also. The torques are 0 there too. But if you just sneeze next to it, it's gonna flip. You guys see that? Just under any kind of thing, you just put a marble in there on the edge, and it's gonna stay. I mean, because this extends to both sides, so of course it goes to the other. This is a repetitive cyclic. I mean, that's property of the sine, which is periodic function.
So would the top point be unstable?
I'm sorry?
Would the top point be unstable?
Except the top is stability, is stable, but metastable, I should call it, not unstable. Any point in here is unstable actually. If you put the bar magnet and the dipole in such a way that there is an angle, any other angle other than 0 is not a permanent stable position. But if you put it on the 180-degree angle, they're going to stay there. It's going to stay there as long as there is not a slight shaking anywhere. It's going to stay there. But with the slight shake anywhere, it's going to flip and go back to 0 degree. You guys see that? So that's basically the essence of the motor. Okay? That is really the heart of how the motor works. If we go back on top in here and look at the motor, so think about this as they have a bar magnet somewhere in here. Okay? And depending on how this orientation is, so as it's moving, it wants to be parallel. The mu and b wants them to be parallel. And as they become parallel because of actually of the inertia, they continue moving, and this will continue going on and on and on and on and on and on. And that's how the principle of the motor works. Okay? It all has to do with the energy. So I think some of the homework problems have to do with that. Let me look at the homework problem. You guys want to take, I think we probably have to cancel lecture today because we took a lot of time in here doing this thing. So do you guys want to come later on at 12 or not?
Yeah, sure.
Okay, I have a problem in here. What is this one? Is problem 15 also part of the homework or not? If you look at it in here.
It's 14, 19, 40,
no,
51.
15 is not, yeah, 15. What is 19 in here? Okay, 19, you guys, okay, 19, it gives you an experiment with cosmic rays, a vertical beam of particles that have a charge of magnitude 3e and mass 12 times the mass of the proton. That's, of course, carbon. Carbon is 12 times the mass of the, unless it's another isotope of another element next to carbon, where the number of neutrons and protons are is actually different isotope, then actually this is carbon if the protons are actually 6 and the neutrons are 6. That's carbon 12. So that's question number 27. So basically, think about it. You have carbon in here. Somehow it has a, it was stripped of 3 of its electrons, so it's running with only 1 electron in the outer shell, and it's coming down as part of the cosmic radiation, and or it was somehow ionized in the atmosphere by cosmic radiation, and now it's lost 3 of its electrons. And now you put the whole thing into a magnetic field of 0.25 Tesla, okay? And is bent in a semicircle of diameter 95 centimeters. You know, this number also of Tesla, you have to be very careful with it. I mean, I know I have seen actually one of the problems that were posted sometime with like the magnetic field 100 Tesla or something like that. That is nonsense. In practice, very hard, very, very costly to reach even, I mean, in the super accelerators, they probably do a few tens of Teslas, but not that much. So 0.25 Tesla is a very strong magnetic field. So if you see an exam problem with 100 Tesla or 500 Tesla or 1,000 Tesla, that doesn't make sense at all, in practice at least, okay? Maybe it's a math problem. So this is fine. So this is 0.25 Tesla. And the particle, of course, is bent into a circular path. So the particle comes in, and because it's, if you see the problem, you see that let me draw the problem so that you can see what I'm looking at. Of course, in this discussion I'm doing right now, I'm not going in depth as much as where I did it in lecture, okay, on those YouTube videos. I hope that you guys have a time to read the chapter, go through those videos if you need to, make sure you have a full understanding of all of these things, and you're ready to do the problem. So this is the problem. The magnetic field, first of all, is coming out of the surface. I'm going to draw a point in here to show that it's actually coming out of the surface, not going into the surface, you see. The magnetic field is coming out of the surface. I probably should have drawn them with bigger dots. Okay, let's do this. So this is the magnetic field, okay? Coming out of the surface in here. And, hey, Winter, you're here. Good morning. Okay, let me mark you as present. Okay, so basically the particle comes in, okay, and it's bent this way, okay, and they give you the radius of curvature is 95 centimeters, okay, and it's a 3e. Basically, the charge on it is 3e. And let's look at the question here from the homework. Where is it? And the mass is 12 times the mass of the proton, and it's been that way. Find the speed of the particle and the sign of their charge. Is this going to be a positive or negative charge? Okay. So we need to find the speed. They gave us the magnetic field being 0.25 Tesla. And they gave us R. Okay. Give us the mass, which is 12 that of the proton. Okay. And what else did we say they gave us in here? Okay, that's all they gave us. So they want us to find the sign of the charge. Okay. I hope that all of you are awake, because I have something for you guys in here. Okay, I want you to all vote for me. Think about it first of the sign. Let me tell you again how this looks like. I want everybody to be paying attention here. So use your right hand rule. V is going down, the magnetic field is coming up, and we know which way the particle bends. Based on that, you're going to tell me if the charge is positive or negative. You guys see the poll in there?
So it's curving with the dashed line?
Yeah, it's curving with the dashed line. Basically, it's going. This is how the particle ended up going.
So it's going to be negative?
I don't know. You're going to tell me. You're going to vote. Do you guys see the polling?
No.
On what? On Canvas or what?
On the discussion thing. There is a on the Zoom itself. There should be a poll.
Yeah, I don't see it.
Yeah.
No, there's nothing.
Just, it should be on the poll. If you can, just go to the chat and tell me, okay? Don't put question marks in there. I see somebody already locked his or her vote. Of course, you're going to get grade for participation, but it doesn't matter if you get it right or wrong. We're going to discuss the solution to this question. There's somebody who couldn't. Okay, I saw the poll and voted. Okay, that's fine. Okay, Winter just came in, probably didn't follow the discussion that we had a big time on. If Tim, you can see, just vote in there, please. Vote in the. So how many people? I'm gonna take somebody at random, okay, and you're gonna tell me why, okay? I like Julian's answer.
Yeah, I just picked it because he did.
Okay. Okay, Gareth.
We'll have
Can you-
Julian answer.
Okay, I need somebody to tell me why. Okay, so we're going to end the polling in here, okay? So it seems like everybody had a chance to, okay? Okay. So Gareth, can you tell me why do you think it's going to be negative? Okay, let me see if I can see your. You can come if you have video. You can go on video. Okay, explain it. Okay.
It's a guess.
That's not acceptable. Of course, it's a 50-50 chance. And somebody else said, I saw some people, I started trend negative, everybody followed me. So it's like, follow the leader. Can you think of a reason, Gareth? And let's work on it together, okay? You know the resultant, yes or no? You know which way the force is bending, correct?
Correct.
And it's going to the left, okay? So we know what this side of the, basically of the end outcome is. And we know also the first part. So what we're missing in here is so basically let's write it down. So it's Q, oops, I cannot write in here. Let me get this thing in here out of the way. So we have Q, V cross B equals to F. We know everything in this expression except Q, the sign of Q. Okay. V is coming down, correct? Yes? I want you guys to be with me here because we want to work on this. Okay. We know B is coming out, okay? So this is how it looks like so far to me, at least, okay? B is pointing toward the wall. And V is coming down, correct?
Correct.
Yes?
Yep.
So if I do it this way, it's going to be pointing, the force V cross B is pointing to the other side. If you do it with me, yes?
Yeah.
Okay, so now if I multiply by a negative number, it's going to be in the proper direction. It's going to be pointing this way. It was pointing, at least in my room, toward the window. Now it's pointing toward the other side, toward the door, when I multiply by a negative number.
Okay.
So again, V is coming down. You start always with the first term in the cross product. V is coming down. The V is pointing away from the screen. It's coming out of the screen. If I just follow that, V cross B is going to be pointing to this side. But according to my screen, it's pointing in the opposite direction. So I have to multiply by a negative number. So the correct answer is negative. Does everybody agree?
Makes sense.
I agree.
Okay, very good. Practice this as much as you can because this is actually a simple situation. It gets very, very complicated very quickly if you're not paying too close attention to this thing. Then find the speed of the particle, and everything else is given by, I think, some notes on top in there. So it's going to be the cyclotron motion is given by, what is it? It's the beginning, actually, toward the beginning. That's this expression. We have R, we have the mass, we have Q, the charge, which is 3 times the charge of the electron, and we have B, they gave us B. So all they want now is V. You guys see that this expression will answer the question?
Yeah.
All you have to do is just plug in the numbers in here. Make sure you use 12 times the mass of the proton. So you need to know how much the mass of the proton is. And you have the magnetic field, you have the charge with 3 times that of the electron, and you have the radius given to you 0.925 or 95 centimeters. Make sure everything is in SI, and you should find the answer to the question how big V is. Okay. And is it reasonable to ignore the gravity? Now you know what the mass is. It's 3 times the mass of the proton, and the mass of the proton is 10 times to the negative 27. 12 times that number. So 12 times that number is still a very, very small number. So 3 times 10 to the negative 27 times the mass of the proton, which is 1.9 or 1.6 or something like that. So you do the algebra and you multiply it by 9.8. 9.8 is the gravity, or 10 meter per second squared. This is still a very, very tiny number. Now, all you have to do is make sure that this force that you're going to be dealing with is many orders of magnitude bigger. Otherwise, it's not reasonable to ignore gravity. So this depends on the number you end up with from part A. You're going to find the velocity in there. You're going to find, once you find the velocity, you're going to find the force that you actually have in there. Once you have the force, now you're back in business and saying that, hey, this force is way big, therefore gravity can be justifiably ignored, or the force is of comparable order, actually smaller than the gravity, therefore this is not justified. So this depends on how much numbers you get in there. Now, this is a big question. Actually, we need to plug in the numbers in here because I need to find what V is. I need you guys to work with me on this in here. So V is going to be equal to, from that expression, remember, it's going to be, what is it? Q times R times B divided by M. Did I get this expression correct? QR. So D is RQB divided by M, yes. QRB divided by M. So Q was given to be 3 times the mass of the proton, and the mass of the proton is 1.6 times 10 to the negative 19. I'm gonna write it down, okay? I don't want to run out of space in there. Okay, so let's write these numbers in here together. So 3 times 1.6 times 10 to the negative 19. Why I'm saying that? Because it's extremely important I don't end up with relativistic or higher than extreme high velocity. So when you're calculating this kind of, when you're dealing with elementary particles, and there are a lot of problems in this chapter that deal with protons and electrons and things like that, you have to make sure you have some number that makes sense. Otherwise, you have a problem. The radius, they say, is 0.95. The magnetic field is 0.25 divided by the mass is that of the electron times 12, proton times 12. So it's 12 times 1.667 to be more specific, times 10 to the negative 27. Did I miss something in here? Yeah. This number is big. Do you guys see that this number is big? Because I have 10 to the negative 27 downstairs, and I have 10 to the negative 19 upstairs. So when the 10 to the negative 7, it's a huge number. It's 10 to the power 8 already. So, and that is 100 million meters per second. Speed of light is 300 million meters per second. So we better be careful in here. We're dealing with very close from the speed of light. Do you guys see that? That's why it's very important when you're dealing with a problem to make sure that your answer makes sense. Otherwise, the problem is just a futile problem. So 3, I'm going to ignore these two numbers, although they are not exactly the same number, slightly off. So I'm going to just approximately say that they are very close to one another. 3 divided by 12 is 4 in the denominator. 1 over 4 in here, so this is 16 actually. And 0.95 is just 1. 1/16 of roughly, I don't know, probably I made an estimate in here, error somewhere, times 10 to the power 8, okay? Did I make a mistake somewhere? Can anybody correct it? So the charge is 3 times that of the electron.
Are you using the 15 edition book?
Sorry?
Is that the question from the 15 edition or 14?
I'm dealing with always the 14th edition. 14th edition. So the problem is 19. It says in an experiment with cosmic rays, a vertical beam of particles that have a charge of magnitude 3e and mass 12 times the mass of the proton enters a uniform horizontal magnetic field of 0.25 Tesla and is bent in a semicircular radius. Oh, the diameter. They didn't give us the radius. I'm sorry. They gave us the diameter. So this is not R. So I have to divide that by 2 again. That's good. So they gave us the diameter to be 95 centimeters, not the radius to be that much. So I need to divide that number by 2, find the speed of the particle and the size of the charge. So is it reasonable to ignore gravity? So I didn't talk about the force yet. Let me continue with the velocity v. So this number is actually half that. So this is 50 centimeters, okay? 0.5, roughly, okay? So this number seems to be good because this number is less than that of the speed of light. You guys understand what I was worried about in here? You check the mass of the proton though.
I think it's 2.01 times 10 to the negative 26.
26. Oh, that's good. That's the number then. 2 times 10 to 2 is the same thing as 1.7. So I'm not going to worry about that for right now. Okay. It's in here. That's going to be an issue. So this is not 10 to the power 27. Are you sure? Mass of proton.
I think it's actually 1.67.
No, it's 167 10 to the negative 27. I had to correct it.
Oh, yeah.
Okay.
Oh no, Aaron.
So it was correct the way we had it. So I guess the number was fine. So, but the problem is not there. I mean, I wanted to make sure that you guys are. So this was correct, 27 and 1.67, and the charge is 1.6 something 10 to the negative 19. So as long as you end up with a number less than the speed of light, you're fine. Okay. As a matter of fact, I can find what the beta is by dividing this one by the. By dividing this velocity by the speed of light and putting it in the expression that is normally used in here, and to find what is the relativity correction. When you're dealing with high speeds in here, and remember, part of my solutions always doesn't make sense, although we didn't take relativity. You have to be careful in here. Make sure that you find some meaningful numbers. This number of velocity has to be within that range. So if somebody throws in some nonsense numbers, a huge magnetic field in here, for example, it tells you, hey, this particle seems to have, what is the magnetic field in here? Yeah, this expression here is 100 Tesla or 1,000 Tesla or something like that, instead of 0.25 in here, and throws in some here that don't make sense for the radius. For example, the radius is bent in such a way that this number will end up being much higher number than what it is. Did I, hold on, I think I made a mistake somewhere in the conversion here. Let me check to make sure that we didn't do something wrong. There's that expression here. So R times Q times B divided by M. Yeah, that's correct. That's what the velocity is. Unless that expression that we relied on was wrong. And that is coming from Newton's law, which is Q times B times R. Yeah, that's correct. Everything is fine. So yeah, I will make sure that when you end up with numbers like this one, this is a well-known fact. You don't need to take physics 252 to worry about it. That everybody now knows. Anybody who took general physics or even watching any kind of thing on YouTube or at home on TV or something like that, they know that nothing can travel faster than the speed of light. And make sure that at least your answers make sense. Okay, that's part of the things that you can do as part of your discussion in here. And the other part, of course, in here, you just neglected, actually, the problem told you to neglect gravity. Does it make sense to do that? In other words, once I find what this velocity is, I can plug it into Q times V times B and see if this force is much higher than mg. If it is much higher than mg, then I'm in business. If not, then I can say, hey, this discussion really was not 100% correct. Okay? This is the reason actually why I am not too focused on when we're doing physics 2 on Hall effect, because it doesn't make sense really to treat it in terms of classical mechanics. This went on for 2.5 hours. I think we should really pause here and come back in about probably half an hour or something. You guys agree? so that somebody can go and eat and things like that, and we'll meet again.
I love it.
Okay.
What time? At 11?
When is our class start? 11 o'clock? Yes, we start at 11. Yes, we go to the other session. Okay, we start the other one. Okay.
Okay. All right.
Okay. Thank you, guys.
Mhm.
Okay. All right.